So far we've talked about first-order differential equations, and we've solved them using separable methods, linear methods, as well as substitution methods. The two substitution methods we've used are homogeneous, which turns into a separable equation, and Bernoulli, which turns into a linear. We also talked about solving things using Laplace transforms. That could have been any order. We did up to second-order differential equations. And we're going to get into more detailed uses of Laplace later in the semester. But right now I want to focus on non-Laplace methods of solving second-order differential equations. We're going to start off with solving a particular type of second-order differential equations. It's going to be what's called the homogeneous case. Notice this is that same word that I've been pronouncing as homogeneous for the substitution method. These two uses of the words have absolutely nothing to do with each other. What it means in this case is the following. Homogeneous means what the differential equation equals is 0. That is, there is no forcing function. There is no function on the right-hand side of the equal sign. So the first thing we're going to do when looking at this is guess a solution. Let's guess the solution to this is, I don't know, one that we've used a lot. Let's call it e to the rt. There seem to have been a lot of solutions where the solution was e to the something. So I'm going to guess that that equation matches and solves this differential equation. Students don't always like when we guess something like this, but let's take this as a guess and see if it actually works out for us. Just like before, to substitute this back into our differential equation, we're going to have to find the first derivative and the second derivative. Once we do that, we're going to go ahead and plug that into our differential equation. Once I do that, I see that I can go ahead and factor out that e to the rt since it's in all three terms. What I have left with is ar squared plus br plus c, and all of that equals 0. I can use the zero factor property to tell me that either e to the rt is equal to 0 or the rest is equal to 0. And if I remember what my exponential function looks like, I know that the function e to the rt can never equal 0. So that means this factor is what must equal 0. This equation is known as either the auxiliary equation or the characteristic equation. And what we can do is use this to solve for r. That is, we want to find what values of r make this true, because the a, b, and c are just constants that are given to me in my original differential equation. So, what do we do to solve a quadratic? Well, that's right, we're going to use the quadratic equation. So I'll always get solutions for r in this form. And if we remember anything about quadratic equations, we know that we get three types of solutions for this. We can either get two real solutions, and I'm also going to throw in the word distinct, meaning two different real solutions. We can also get one solution. That one real solution, we're actually going to call it a repeated real. It's the same value twice. And finally, we can get two complex solutions. Not only are they complex, they're going to be complex conjugates. That is, they're going to be in the form of alpha plus or minus beta I. The real portion will be the same, the imaginary portion will be the same. All that's different between the two solutions is one is adding the imaginary portion and one is subtracting it. Let's first focus on the two real or two distinct solutions. I'll get two solutions, an R1 and an R2, and those correspond to the independent solutions. y1 equals e to the r1t and y2 is equal to e to the r2t. Let's look at an actual example of this. Let's use this as an example. Y double prime minus 5y prime minus 6y equals 0. We're going to skip the guess of the e to the rt. We're going to go straight instead to the auxiliary equation. And that would be r squared minus 5r minus 6 equals 0. Notice how it matches with my original differential equation. The second derivative leads to the r squared, the first derivative leads to the r, and when it's just y by itself, there's no r. It's the same thing as r to the 0th power, if you think of the fact that y is the 0th derivative of y. So let's go ahead and solve this. This one we don't have to resort to the quadratic equation because this is easily factorable. this leads to two different values for r. r1 is 6 and r2 is equal to -1. Notice it doesn't matter which one you call r1 and which one you call r2. So my first solution would be e to the 6t, and my second solution would be e to the -t. So where do we go with this? Well, I'm going to just state this right now and give the why in a follow-up video. But you should take away from this that if I have two distinct real roots, that is, if the auxiliary equation has distinct real roots, r1 and r2, then as I've just stated, y1 e to the r1t and y2 e to the r2t are both solutions. However, we can combine them using what's called the superposition principle and state that y of t is equal to c1 e to the r1t plus a different constant c2 e to the r2t, and that's known as our general solution. So if I have two distinct real roots, this is my general solution to the differential equation.